Okay, so we're talking about method of reduction of order. The premise is simple. If you have a second order homogeneous linear differential equation and you know a solution y1, then you're going to try to use this solution y1 to find a solution y2. Now if you got constant coefficient equations, normally it's not going to make any difference, but it does when you have a repeated root. Okay, so anyhow, we have solution y1 of the second order equation. We're going to assume a second independent solution, u of t, y1 of t. Then we're going to see if we can figure out what u of t might work to give us a second solution of the equation. Then we would have a complete solution set because, of course, this is a second order equation. So a simple example is just a very simple constant coefficient equation that we all know how to solve, and we know what to do with this. Okay, we have an et cetera here. You do the characteristic equation, you solve for r, you get r equals -3. It's a repeated real root. Well, then you know that e to the -3t and t e to the -3t are solutions because that's what I told you to do. And I said, well, delay reduction of order until a little bit later. Well, it's time to do reduction of order and see why that works, or at least see how we can arrive at that other than just by trial and error. Okay, so y1 of t is e to the -3t. That's a solution. We're going to assume a solution, just like we said here. We're going to assume the solution u of t, y1 of t. U of t, y1 of t, well, that's going to be u of t, e to the -3t. So we have y2 of t equals u of t, e to the -3t. There's our second solution, but it's not going to do as much good until we find what that u of t is. Well, we just proceed to plug this solution into the equation. Okay, we take its derivatives, and that's very straightforward. We've done this. We did this, something very similar to this, when we developed a variation of parameters. Now, usually we do reduction of order before variation of parameters. It's just we happen to get the variation of parameters first. Okay? But you see some similarities, and if you look back at how the variation of parameters is derived, you see that we have very similar premises, except that with variation of parameters, we have two solutions to a second order equation, and we're trying to find a particular solution by doing kind of a linear combination of our two solutions, but it's not a linear combination because we're going to do like a u1 of t, y1 of t plus u2 of t, y2 of t. Now that's what we did with variation of parameters, and that hopefully is a little bit familiar to you. Just to put this in context. Anyhow, back to this equation, what we do here is we just do these derivatives and then plug them back in, and we get this mess, okay? And it's very straightforward. You can plug these in. I don't have to explain where everything came from. Now we did a first pass through this, and I explained it because I wanted to be sure it was right, and miraculously it was. Okay, then we put all this together. This equals 0. Well, e to the -3t can't be 0, so this has to be 0. Yeah, another way of looking at it is e to the -3t can't be 0, so we divide both sides by e to the -3t. But we use the multiplication property, the zero property of multiplication, and determine that this has to be 0. And when we simplify this expression here, everything goes away. We've got a -6u prime and a +6u prime. We got a 9u and a 9u, but then we got a -18u here, so the u primes and the u's go away. We get u double prime equals 0, and that's always going to happen for constant coefficient equation with repeated roots. So that u is going to have to be what? Just a linear function. I'll use capital A t plus b, where capital A and b are arbitrary. Now all we're trying to do is we're trying to find some u to put in here. We could put in any linear function. 48t plus 936. But the simplest thing to put in is just plain old t. A and b could be any numbers. and any numbers would work. It would give us a perfectly good solution, but the simplest solution we get is to let A and B be 0. Okay, there's no initial condition, no restriction on these parameters. So we make the simplest possible choice. We let u equal t so that y1, and I wrote that wrong, it's y2, equals te to the negative 3t. There's our u, y1 of t. And now we've got our solution set, and that explains how we could have arrived at this thing about putting the t in front of the first solution to get the second solution with repeated roots. Okay, well, that's all great, but question arises, what happens if we don't have a constant coefficient equation? And it turns out that we have a method for dealing with that. The reduction of order, but it's a little more general. Okay, so if we have the general equation, and that equation is y double prime plus p of ty prime plus q of ty equals 0. We have a solution y1 of t. Well, we're going to assume a second solution. Second solution would be y2 of t equals u of t, y1 of t. Well, we're going to do the same thing that we did before, but of course now we don't have a specific function for y1. We do our first derivative, our second derivative, plug it all in, and we get this. Now that plug-in is very straightforward. The next part of it isn't quite as straightforward. So, and I rearranged this like so. It wasn't a particularly good choice of root arrangement, but this is what you do when you try to derive something. You don't just memorize how it goes along. You try to see how would I have done this if I'd been the one discovering the method, okay? And it probably wouldn't have gone this smoothly. Probably didn't when the method was discovered. Okay, so we rearrange this as this, and you can check and see that every one of the terms you get here matches a term up here. The point is that the original equation, and this is very similar to what happened in variation of parameters, the original equation is sitting here, hiding. All you got to do is find it, okay? It's like a little bit of a puzzle where you're trying to find Waldo or whatever. So Waldo's here, here, and here, okay, original equation. Because why? Well, here's p of t times u times y1 prime. Well, there's a p of t y1 prime and a u. Here's a q of t y1 and a u. And here is a u with a y1 double prime. Now it's important that we have just u with each of these. That's kind of what you end up looking for. Okay, the u terms turn out to, if you multiply this by this by this, and write down this, you get u times y1 double prime plus p of t y1 prime plus q of t y1. This is the left-hand side of the original equation, and we know it's 0 because y1 is a solution. So here it is, and we can comment that this much is just 0. And that leaves us with this. Now I didn't write it down real well. It reads y1 u1 double prime multiplied by the quantity 2u prime plus p of t u prime times y1 prime. Okay? Now, even if you don't see it there, once you realize that these terms go away, this is what you're left with, and it can be written like this. Okay? So if you just remove these three terms because of this, and look at what you have here, you see that you're going to get this. Okay? So it's really kind of unnecessary to write all this down. But there it is. So where does that leave us? Well, notice that we don't have any u's left. All the u's went away with this thing. Okay? And we just have a u prime and a u double prime. So this is really just a first order equation in U prime. So we let W equal U prime, and it's not U1 prime, just U prime. And we rewrite the equation with W here and W prime here, and there it is. And this is just a first order linear equation in W. Well, the solution to this equation, did this step, let's make sure that's separate. Okay, we divide by y1, and we can do that because y1 is a solution to this equation. It's not 0, okay? Now, I guess technically it could be a function that might equal 0 at some point, and if it is, we probably ought to write okay, the domain of this equation is all t such that y1 of t is not equal to 0. Okay. And I guess I should write that as a side note. So you might have a split domain if y1 has one or more zeros. Okay. The solution, and that's not going to happen often, but it could. I think it could. I don't think I've encountered it, but okay. Solution to this equation, well, that's like a w prime plus a p of tw equals 0. You do e to the negative capital P of t, like we do the first thing we learned probably, or one of the very early things we learned. You're going to integrate this, and you're going to do e to the negative integral. And there's your w function. So if you can integrate this, okay, then you get a closed form solution for w, and then all you got to do is integrate that to find u, because of course u is what you're after, and all you have here is w, which is a derivative of u. So there it is. Okay, and we call this reduction of order. Again, this equation has order 1. So you have your second order equation. Reduced to order 1. And that occurs because we have one solution. Okay, having one solution to this equation allows us by this method to get an equation of reduced order, and then this is the only equation we have to solve. Then of course there's a question, can you integrate this, and can you integrate what you get when you integrate that? Okay? So you have a solution, it's just, can you express it in closed form? So you know the solution is basically an integral of this, which involves an integral. And you do have to deal with that.